Okay, so we're going to have a look at the acidic nature of the aqueous aluminium ions. And just to start with, you just need to kind of look back at what we talked about when we were talking about dissolving way back in term one. And if you remember, we talked about the ions. For example, if you dissolve sodium chloride, we talked about the sodium positive ion being surrounded by the waters. So there's the sodium ion and there are the waters. And because the sodium ion is positively charged, it's the D minus end of water that surrounds the sodium ion. And if you remember at the time, we said that 6 waters forming this kind of weak attractive force with the sodium is enough to provide enough energy to kind of overcome the electrostatic force of attraction between that sodium and the chloride ions that surround it in the lattice structure. And of course, similarly, when we're looking at the chloride ions, because that's negatively charged, it's the D plus end of the water molecule that forms an attractive force with chloride. Similarly, as energy is given out as many waters surround the chloride, it's enough to overcome the electrostatic force of attraction between the chloride and water. Now, what we kind of haven't mentioned, or if I kind of talk about it in terms of aluminium, there's a whole unit basically called complex ions, which we don't do until we're in year 2. However, in order to understand the acidic nature of the kind of dissolved aluminium 3 plus ions, we need to touch on what a complex ion is. And a dissolved aluminium ion can be written in one of 3 ways. So it can be written like that, which is the one that you're probably most familiar with. It could also be written like this. Now, this is very similar to what we were talking about with the sodium ions with water up here. There is, however, a slight difference with this one here. And that's the fact that the water molecules, as they surround the aluminium ion, it forms a dative covalent bond. And if you, I'll just zoom in a little bit. If you remember, on all of the kind of water molecules, there's 2 lone pairs on the oxygens that are around there. And one of the pairs of oxygens on the oxygen in water forms a dative covalent bond with the aluminium ion. Okay, and of course that's going to happen with all of these as we go around here. So there's a dative covalent bond. Now, the other thing that happens with this, if I just get rid of all of that, is, actually I'll come back to that in a minute. Let's just talk about all the ways that we can write this. So we can write this. We can write this as more of a kind of structural formula, really, if I kind of zoom it back out again. So we can actually write it like this. So we've got the aluminium with 6 waters surrounding it. And then we've got the kind of square brackets here, which correspond to those square brackets there. And then we've got the 3 plus charge on the outside of the brackets, which is what we've got here. So basically, all 3 of these are exactly the same, and it often depends on which bit of chemistry that we're doing. So this is what is really going on, where we've got 6 waters forming dative covalent bonds using a lone pair of electrons on an oxygen in a water molecule. But it could just as easily be written like that, and that's how we tend to think of it up till now anyway. That dissolved aluminium 3 plus ions, we just call it aqueous. But of course we could write it like that as well, and really this and this and this and this they're all one in the same. And as I say, it depends on how you tend to think about it. Now, if we understand that, we can have a think about why the aluminium 3 plus ion is actually slightly acidic when it's in water. And I'll just zoom up a little bit in here so we can have a look at this. So what you've got to remember is that this aluminium ion in here has a 3 plus charge, and it's very, very small. And because it's small and has a very high charge, it has this tendency to pull electrons towards it. And what it does, if I just pick one of the waters, I'll pick this bottom one here, it pulls electrons from the dative covalent bond towards itself. And because the aluminium is so highly charged, that effect is felt all the way through the kind of water molecule. So it's pulled in that way from there and there as well. So all of the oxygen-hydrogen bonds in the waters in this, what we call a complex ion here, they're actually slightly weaker than the normal oxygen-hydrogen bond in water because the electrons have been pulled towards the aluminium all the way through the molecule. So because the bond here, and in fact in all of the oxygen-hydrogens around in this complex ion are slightly weaker, they have a tendency to break. And because they have a tendency to break, if I use a curly arrow, which is this curly arrow here, and oxygen being the most electronegative, you can see that when the bond breaks, the pair of electrons goes on the oxygen, and essentially what we've released here, if I just try and zoom that back down again, is a hydrogen ion. And of course we know, don't we, that things that release hydrogen ions, basically proton donors, are acids. So this hydrogen here has formed this hydrogen ion over here. The pair of electrons has gone from there to there, which gives us this. Now this thing here, if I take it off the aluminium and put the pair of electrons that are in this dative covalent bond back on the oxygen, is basically a hydroxide ion. And if you think about that being a hydroxide ion, the effect of that is going to be that the charge is going to go down by 1. So it started off as 3+. I've lost a plus, a hydrogen ion, which basically means it's going to be 2+. Or, if you prefer to think about it as a hydroxide on there, with one of the lone pairs being used as a bond to the aluminium ion in the middle. This is now slightly different, okay? And this is what we mean by the acidic nature of the the aluminium ion in water. Due to the high charge of the aluminium ion, the electrons are pulled through all of the water molecules, weakening the oxygen-hydrogen bond, which means just naturally in water, just the kind of ambient temperature of these ions in water, they dissociate their a proton quite readily, and there's that proton there. It's very often easier to think about it as an equilibria because it is a weak acid. It only does this by a very small amount. So very often we'll think about this as if it is in equilibria because, like any equilibria, if I add hydrogen ions to this, the equilibria will shift that way. And alternatively, just to kind of stick with the equilibria stuff, if I add hydroxide ions to this, that reacts with the hydrogen ions there, which will form water. So essentially I'm losing those, and the equilibria shifts that way in order